Welcome back, everyone. So last time we talked about semantic analysis and how to implement it in Uranium. I showed you my implementation for my language called Psi, and in particular, most of our time was spent with how to implement the typing of expressions. This time we're going to do the rest of it, starting with types. So this is very similar to the rule for references. So you remember for a reference, we would look up in the scopes where the reference was defined. So it could have been a variable or a method name. Here we are always looking for a type. So a simple type is a type that occurs on its own. It's a simple name. So it could be int or it could be string, for instance. And these types have two sources. Either they are types that are defined by default in the root scope, or they are types introduced by user when he declares the structure. So we capture the scope, we create a rule, we compute nothing because what we will do is define a nested rule. So just like for a variable, we look up name. If we find nothing, we emit an error. If we do find something, we need to verify that the thing that we found was a type. Let me explain. My language only has one namespace, meaning that variables, types, functions, they all share the same namespace. So you cannot have a variable that has the same name as a function, and you cannot have a type that's the same as a function. Or rather, you can have that, but then they will hide each other. So the thing that is in the innermost scope will hide the definition that is in the outer scope. So this is something you need to think about for your language. Do you want to have a single namespace, like in my language, or separate namespaces? For instance, in Java, there is 3 separate namespaces. You have a namespace for classes, for types basically, one namespace for variables and values, and one namespace for methods. But this also has a flip side, which is that when you want to use a type or a function as a value, you need to devise a special syntax. So for instance, in Java, I cannot pass a type to a function. I cannot write this. Instead, I have to write string.class to get a type representation. A similar thing for a method. I cannot say I want to pass this method. I cannot pass simple type like this. I need to use this notation. We do get the declaration and we'll verify it's a type declaration. So it's a type declaration if it's a structure declaration or if it's a synthetic declaration. So this is a declaration available by default that's defined in the root scope. And if it's a synthetic declaration, we also need to check the type of declaration is type. If that isn't true, then we also emit an error. Otherwise, we have resolved the type name to a type declaration, and then we simply copy the declared attribute of declaration to the value attribute of that node. So why do we use the name value and not the name type? Well, that's for my own convenience, because I could have called this type, but the name type was already used for the type of expressions, and it's also used for the declarations, for the type of the thing being introduced. Declare, on the other hand, is the type being introduced by a declaration. So remember that if you have a structured declaration in my language, like here, this will get a type attribute, which will be the type, because pair is a type. But it will also get a declared attribute, and that will be valued to pair. Let me remind you how things work for the default types. So these types are defined here. Okay, so that's not special. As you can see, they are defined with a synthetic type declaration. However, here below in the initializer, in the constructor of the root scope, we actually pass a reactor to that, and we set some attributes. And notably, we set the type attributes. Like I said, a type will always have its type attribute set to type, and also the declared attribute. Okay, so you can see that indeed void gets void type, string gets string type, etc. We also type the default variable, so true is a boolean, so is false, and null as null type, of course. And even the print function gets its own function type. So it has a string parameter and it returns a string. Okay, so in my language, the print function not only prints the string to the standard output, but also returns the string. The next thing we're talking about is the array type. This would be when you have something like this, for instance. This whole thing here, that's an array type. And that's very simple. So you get the component type, you get the value of that type, and once you have that, you can get into the rule and you create a new array type that wraps that component type. Very simple. We've seen that function just a minute ago. And the following function is assignable to, is comparable to, and common supertype. We've all seen them in the previous video. The point here is that when you make your type system, you will need to think about what can be assigned to what can be compared with what, which types are compatible, and when are they compatible. And you'll probably have to implement a set of functions like this to take care of this issue, and you might have to use them in a bunch of places. So next we get to scopes. And this is also something we talked about last time. So pub scope is the function that is called by the post visit. So after the children have been visited, you visit the parent, and it resets the scope to the parent scope. This is only called for nodes that actually introduce a scope, which is the root node, the block node, and the function declaration node. Talk about the devil, the root node. This is the first thing we actually visit when we visit D3. And so at that point, the scope is null, which we verify by an assertion, and then we set the scope to the root scope. Notice how we pass the reactor here. That's what I just showed you, That's when it will define the attributes and the default types and the default variables. For every node that introduces a scope, we also need to set its scope attribute to scope. Now we talk about block. So the first thing we do is that we create a new scope. We push a new scope if you want, and we use the current scope as the parent. We set the scope attribute, same thing as before. And the other thing that we have to do for block is see if they unconditionally return. And for that, we'll set the returns attribute to a boolean. So when does a block return? Basically, it returns if it contains a return. So this is an empty block, it does not return. This is a block that returns. This is not a block that returns, okay? Why? Because it only returns if the condition is true. So this condition here is always true, but it could be like this. So this block does not return because if this is not true, it will not return. The language is not, well, the semantic analysis is not smart enough. So this will also be considered as non-returning, even though in practice it always returns. So we don't go into the expression and we don't try to evaluate it to see if it's always true. We could do it, and in fact, Java does it, okay? Can I actually show you an example of that? Maybe I can. So I'm gonna create a function that returns, say, a boolean. So right now it shows an error because we don't return. If I say if true, return true, this should work. It does still say, okay, it does not work. So Java is not that smart. It is that smart for while statements though. Yes, so now it says it's okay because it knows that we always return. However, if I change something, so if I create a boolean x and I say that it's false, let's even say that it's true. Let's even make it tricky like this. See, now we have this error again. So I don't know if you see it because it's very small. Basically, it's underlined in red and it says missing return. You don't see it, but you can trust me. And what happens is that it cannot ensure that x is always true because it's a field and it's not even final. And so it's not clear that this will be taken to return. And so we really need to put another return statement there to make sure that all code paths return. So that's what we're trying to do here. And our language also does not consider that this does not return also in our language. However, we are smart enough to do this check. So if we see this, then this block is considered to be returning. Okay, that's for the theory. Now, for the practice, how do you compute that? Well, we set the result, the returns attribute, to the result of this condition. So we're using as dependencies the return function, the return value of this function, get returns dependencies, and we will go to see what it does. But basically, it will give us all the node that could potentially return. Okay, so if there are no such node, so if it's 0, then this does not return because no node can return. Then it's failed and does not go there. If, however, there are some node that could return, we stream them and we see if any satisfy the condition. So we just get, and basically you'll see that this is a list of attributes that themselves are returns. Okay, so basically we see if any of those nodes do return, and if any of those do return, then indeed the block does return. So let's see that function. So that function takes a list of children. Okay, and so here we see that the children are the statements that are inside the block. So we stream them, we remove everything that is null, because in some cases we'll call this function with a list that can contain null items. We only keep things that can return or contain a return. So this is defined by this function is return container. So a block can contain returns, a if can contain returns, and a return obviously is also a return. And like I said, we don't do while. So if there's a return in a while, it does not count. We don't care about that. It will not be considered. And like I said, we take all these nodes, we create the returns attribute on it, and we stuff all that in an array that we return. And so that's it basically. You get the theory, you get the practice. This sets returns to true if the block always returns, and otherwise if it's just in a single branch of a if, or if it's in a while or something like that, or if there's no return at all, then it's going to be false.
The next thing we're talking about is variable declarations. So a variable declaration is an inference context. Remember that's to type empty array. A variable declaration introduces a new name, so the name of the variable. So we add that to the scope. We also store the scope in the scope attribute of the node. And the reason we do that is to help with the interpreter later on. So that's kind of a dirty trick. It's not really related to semantic analysis, but sometimes these tricks can be quite convenient. So to derive the type of declaration, well, the type of declaration is simply the value of its type annotation. So if I have this, well, it's the value attribute of this node. Okay, we saw a method called simpleType that derived this. And if it's an array type, there was a method called arrayType. The next thing we want to do is to check if the type of the right-hand side that we inferred matches the type of the annotation. Okay, and so this is this rule here. So this is the type of the right-hand side, and this is the value of the type annotation. So we just get them and check that the actual type, so the type of the right-hand side, is assignable to the type annotation. And if they're not, we report an error. So the next thing is field declarations. And these are just variable declarations without the identifier. And so the only thing we need to do is copy the value of the type annotation to the type attribute. Okay, so there's a structure declaration here. We just need to say that A as type int. The next thing is parameters, and parameters are basically variable declarations inside a function signature. The handling is going to be the same. We declare the parameter inside the scope, and this scope is a scope that is specific for parameters, and it's pushed by the function declaration node. So when you have a function declaration node, it pushes one scope for parameters, and then the body of the function, that's a block. That's the AST node block, and that also pushes a new scope. So there's two scopes. So the type of the declaration is simply the value of the type annotation again. Next, we have function declaration. So like I said, they introduce a scope for parameters, so we do all the usual stuff there. Next, what we want to do here is to derive the type of the function declaration, and that's going to be a function type, okay? Remember, a function type is simply a type is a return type and an array of parameter types. And so the dependencies we need is the type of every parameter and the return type. So we create this array. The first item is going to be the value of the return type annotation. And then each subsequent value is going to be the type of each parameter. So if we take an example, this function is going to have the return type int, and it's going to have one parameter with return type pair. Once we have that, we just extract the values, so all the types for the parameters, and then we create a new function type with the first value that's the return type and all the type for the parameter. The next thing we do has to do with returns. We check the returns attribute for the block, so that's the body of the function, and we check the value of the return type. What happens is that if the return type is not void, because that's the return type that we implicitly assign for functions that do not return values, so the same thing as void methods in Java. So if there's a return type and there's no return statement in the block, that's an error, because how would we know what value to return in that case? So that then we report that error. However, we say here that the actual type of the return value, that's checked in the return statement. And there we also check if actually there is a return value, right? Because we can have a return without a value, or we can have a return with a value. So we haven't talked about structures much, but this is quite simple, so I'll do it now. First of all, we introduce a new name, so we put it in the scope. The type of declaration is type. Why? So a structure declaration is like this. This pair can be used as a value. So I can do something like, I can do this. However, I also introduced a pair type, which I can use as a type annotation, like here. So I need to account for these two things. So the type is type, but also declare a new type, and it's a new structure type for the structure. We are almost done. Now we need to tackle some simple statements. So in the case of the if statement, we want to check that the condition is a Boolean and emit an error if that's not the case. We also want to check whether it returns unconditionally. So remember, we saw this function get returns dependencies and gets you all the children of the node that are able to return. So in this case, it's a true statement and a false statement. And we are going to say that the if statement returns unconditionally if there's two such dependency that can return, and if they all actually return, so their returns attribute is true. So to give you an example, we could have something like this. So this is not good enough because there is no else. So this only returns if the condition is true. But we could also have something like this. And this only returns in the if, so again, it does not return unconditionally. Okay, let's go to while. So this is actually the same as for if, we just check that the condition is a Boolean. Very simple. And the last function we have here is the return statement. So the return statement always returns, so that's very easy. We are going to call this function current function, and what that does is that it walks through the scopes. As you can see here, we iterate on the scope and we take the parent until either we find null, which means we have gone out of the main script, or if we find a fun declaration node, okay? If the node attached to the scope is a fun declaration node. So the idea is that if we're in a function, we're going to find the innermost function that we're in. That's what this does. And if we're not in a function, we're going to return null. So if we're not in a function, we don't do any checks. currently. If we are in a function, we'll distinguish two cases: the case where we return an expression and the case where we don't. So if we don't return an expression, we will simply check that the return type of the function, okay, so it's the type annotation, the return type annotation of the function. We will check that it is void type. If it isn't, then it's an error because we just have a return, but the function wants to return a value. Otherwise, so if we do have an expression, then we actually do the opposite check. If it's void, then we're returning a value when we shouldn't. Otherwise, we check that the value that we return, so that will be actual, and that comes from here. And notice a nice bug here. We used 0 twice, which means that this was always going to succeed because it's going to be the same. So actual is the type of the expression. Formal is the type of the return type notation, and so indeed we check that the expression can be assigned to the return type. And if that's not the case, we return an error. And the rest of the file is simply a utility function that we already saw. We do need, though, to do one last thing, and those are functions that we skipped before. And those have to do with fields. So we want to do field access here, now that we've talked a bit about structures. So the first thing we want to do is get the type of the stem. And so the stem is going to be the thing before the dot. So if I have x.y, the stem is x. And we're going to check, and there are two things that can have fields. So array types can have field, and they can only have one field with this length. So if the type is array, we check if the field is length, and then the type of that, we're going to set the type of that via an inner rule, is going to be an integer. Otherwise, it's an error because the only valid field for arrays is length. Otherwise, it has to be a structure. So if it's not a structure, then we report an error. Okay, here we know that we have a structure. Now we're going to iterate through all the fields in the structure declaration until we find one. And if we find it, then we already typed the field. Okay, this is something we did in a function called field declaration there. And so we just transfer this type to the node, which is a field access node. And if we find the field, we return. If we don't find it, we report an error that we try to access a field that does not exist. The other thing that we skipped before is the constructor. So in my language, I have functions, so I can call a function like this. But imagine I define a structure also called f. Now maybe this function is an integer. I could have said that I'm going to make the constructor behave like a function. So this is going to create a value whose type is f. However, because in my language I want to ultimately be able to pass types and function as value, this would be ambiguous, because what if I did create other function, this? Now the question is, f, is it a function, the constructor, or is f a type, so the structure? So to solve this issue, the decision that I made is that I would use the dollar operator. So basically f here is the name of the structure. So this is a type. But $f, sorry, that's a function, that's the constructor. And this is still a bit in project because my language does not have a representation for function type. You know, ideally, I would like to be able to write a function called f3, and I could pass a function, I could pass a parameter, and that parameter would have a type that looked like, I don't know, maybe something like this. You know, a function that takes anything or returns an integer. At the moment, I cannot write this in the language, but ultimately, I would like to do that. So The idea is that a constructor expression is this thing, and the type of that expression is a function type. Okay, that's the context. So what do? We get the declaration that corresponds to the reference, because a constructor is always called on a reference. Remember that a reference is simply a name. So you can do this, but you can't do this, for instance, or just this. This will be a syntax error in the parser. So we do know that there is a reference, and we get the declaration that the reference refers to. So what you're expecting is that it will refer to a structure declaration. And in fact, if it does not, it's an error, and then report the error. So next thing we want to do is derive the type. Like I said, it's going to be a function type. For this, we need some dependencies, and these dependencies are going to be the type attribute of every declared field in the structure. Once we have that, we get all the values. So we get all the types of all these fields, and we construct a new function type. The return type of the function type is the structure type that we're building, and the parameters is the type of all the fields. Okay, so there's one parameter per field, and the return type is the structure that you construct by basically assigning all the arguments to every field in the structure. And that's it. With that, we've done a complete tour of the semantic analysis of this language, which is a simple language, but not a trivial one. Okay, so there's already quite a bit of stuff there. And I hope this helps you build semantic analysis in your own language. So what have we learned? Well, the main point is that I wanted to give you a feeling for what semantic analysis is and what it's for, and how it can be done in practice. So if you're one of my students, don't be afraid. I'm not going to ask you a question about what I said about the best way to implement while statements. That's not the point. The point is really help you implement in your own language semantic analysis, and so that you have a clear idea when you think semantic analysis, what do we do with that? Okay. In particular, I've shown you the reactive model, which is what's implemented in the Uranium tool. And in this model, there's basically two steps. In the first step, we walk the tree to create rules, which work on attributes. And attributes are made of an AST node and a name. And then once we have created all these rules, we repeatedly execute the rules whose dependencies are met. So at the start, there are some very trivial rules that do not need any dependencies, and we can run those. And then these will create new attributes. They will derive the value of new attributes. And these attributes can be used to run new rules, etc., etc. And hopefully, at the end, we've run everything that we want to run. Is this the most common approach used for semantic analysis? No, actually it is not. Another very common approach is using multiple passes. So that's basically walking the tree multiple times to derive more and more information. The reason I'm showing you this reactive model, despite the fact that it's not super common, is that it's much simpler. So in this model, you do not need to think about data dependency, basically. You just say, I need this data, and the framework will figure it out for you. As you've seen, there's already a lot of stuff that we have to do, okay? It's not a small bit of code, semantic analysis, especially if you have typing in your language. I think it's worth just focusing on that, on what you're actually checking first, instead of thinking of data dependency, because that is a concern that will make everything else much harder, because at any given point, you need to be thinking, oh, do I already have this information? In which order should I derive the information, etc.? It just makes everything much more complicated. That being said, there are elegant designs that use multiple passes. I'm not saying that does not exist, but I think this model, at least to learn, is much simpler. It is also less efficient, so it's not all good. However, I think it's better to first start writing your language like this, and then later, if you want to make your compiler run faster, then you can transition to another model once you already know what you need to compute precisely, and actually what the data dependencies are, because what will happen with a mature language writer is that you start writing a language and you don't do a full specification in advance, okay? You just kind of go with your whim. And as you're coding, you realize that you have data dependencies that you were not aware of. And so you need to rethink all your design. And this can be quite wasteful in terms of engineering effort. So more specifically about what we did in Uranium to create semantic analysis. Mostly we did go bottom up. So for instance, we use sub-expression types to compute types of bigger expressions. And that's, I would say, most of what we did. But sometimes we also had to go top down, so go from higher level nodes down to lower level nodes, like simpler nodes. And an example of that is lexical scopes. Okay, so lexical scope form a hierarchy where they're nested within one another. And we've seen how as we traverse the tree, we create these scopes. And as we go back up the tree, we pop them. So we just remove them. And these scopes, we actually store them in some attributes sometimes. Another example of that was particularly interesting is the inference context, which we use for type inference. So in my language, there's only a single example of type inference, and it's for the empty array. So there's no way to know what the type of that array is, except that if you have some type inference context, like a variable type, and you're assigning this to a variable. Finally, I want to highlight some cases where you need to be a bit creative and use a bit of flexibility that the reactive model gives you. I think the best example of that is when you define rules within rules. Because statically, you're just walking the tree and you do not have the node that you need to define the rule. And typically what you'll do is that you'll use a rule first to get that node. Okay, so it will be the value of an attribute. And then you will use that node as either a dependency or as an exported attribute to create another rule. And so be aware that you can do that because you probably will need to. So something I should really have mentioned sooner, but there's a link to the code that we reviewed in the description of the video and also in the description of the previous one. If you have any trouble with semantic analysis, or if you're working on your own implementation of it, I highly recommend that you go and have a look at the code to see how it's actually working there without me talking over it as a distraction. So that's it for this time. The next topic will be actually running your programs, okay? So one way to do that is to run it in an interpreter. And I don't think I will say much about that because, again, it's mostly engineering. It's even easier than semantic analysis. So I might just highlight some key points, and then I will send you to the interpreter that I wrote for my language I presented in this video. It's actually already in the code that I linked in the description if you already want to have a peek. The other thing I want to talk to you about regarding running languages is how to emit Java bytecode. This is what we're going to see in this course for code generation, because it's pretty simple and it comes with batteries included in a way. You don't have to implement your own garbage collector, for instance. I hope this video has been useful. I will see you all next time and enjoy life in the meantime.